Bismillahirrahmanirrahim. Dear students, welcome to the Electrical Engineering channel. In this lecture, I will discuss classical economic dispatch problem in the presence of losses. So, whenever we have losses in an electrical power network, the coordination equation will become dFi divided by dPgi plus lambda partial PL over partial PGI is equal to lambda. So, this is called incremental fuel cost equation, and here partial PL over partial PGI is actually a measure of the sensitivity of the system losses to an incremental change in the output of the plant I when all other plant outputs are kept fixed. So this is the definition of this term partial PL over partial PGI, and it is the sensitivity of the system loss to an incremental change in the output of the plant I. So this is the expression for the loss power which we derived in our previous lecture, and we can evaluate the derivative of this loss power with respect to Pg1 and the derivative of this loss power with respect to Pg2. These two derivatives will be helpful in calculating the penalty factor, which I will show you, and the incremental fuel cost function for the first generator can be written as partial F1 over partial Pg1 equal to A1 Pg1 plus B1. So the first equation will become A1 Pg1 plus B1 minus lambda plus lambda times partial PL over partial Pg1. So this is the first equation, right? For the first generator, this lambda is taken to the left hand side and it will be minus lambda. So this is minus lambda. And we can take Pg1 as common, and this is the Pg1 term, this is Pg2 term, and the other term is considered as positive and it will be taken to the right hand side. Similarly, we can write the expression for Pg2, and after taking Pg2 as common and rearranging all the terms, for the second generator we will have 2B21 Pg1 plus A2 divided by lambda plus 2B22 Pg2 equal to 1 minus B20 minus B2 divided by lambda. So these two equations can be written in the matrix form. Here we will have Pg1 and Pg2 and their coefficients or multipliers will be written in the matrix, and at the right hand side we will have a column vector with these two terms. Again, these two equations, this one and this one, they can also be written in the summation form as you can see over here. So this is the equation for a two node network or for a network in which we have two generators, Pg1 and Pg2. So if we have total k number of generators in a network, then we will have a k by k matrix over here. We will have a k by 1 column vector over here and a k by 1 column vector over here, and that will be the column vector of the generators Pg1, Pg2 up to Pgk. And for a 2 by 2 matrix, we will have such an equation, and this will correspond to a system in which we have two generators. Now we have to solve these set of equations to calculate these power generations Pg1, Pg2 up to Pgk, and these equations will be solved in an iterative manner, and at the end we must satisfy this constraint. This constraint is called power balance equation, and from this equation we can say that power loss plus power demand must be equal to the total power generation. So that total power generation can be taken to the left hand side, and in that case power generated by k units is equal to power loss plus power delivered to the load. So that is a constraint, and we will solve these set of equations in an iterative manner until the time when we have satisfied this power balance equation. So when this power balance equation is satisfied, iterations will be stopped and the values of Pg1, Pg2 up to Pgk at that instant will be considered as the final values. So this is an iterative problem, and this method is called lambda iteration method. And in the first step, first we have to specify the total load of the network, and that is PD, which is equal to the total load connected at the buses. So J equal to 1 to n PDJ. So if we have n buses at which load is connected, then this summation will be done for those n buses. In the step 2, we have to initialize the value of lambda, and that initial value of lambda can be calculated by this equation in which no loss has been considered. So lambda is equal to AT plus BT. This is the equation of the lambda for a lossless power network. So that will be our initial value of the lambda, and that will be updated after each iteration. Now we have to substitute this value of lambda in equation 2 and then solve the system of linear simultaneous equations to find Pg1, Pg2 up to Pgk. And here you can see this is our equation number 2, and we will substitute that value of lambda over here, and all other coefficients are known to us, so Pg1 and Pg2 can be calculated. So after calculating these power generations, we will check this power balance equation if this equation is satisfied or not, right? So these power generations have been calculated. Next, we will compute the transmission loss, and transmission loss equation is this. And in the step 5, we will evaluate the quantity PGI minus PL, and we will compare it with PD. So this is the constraint that we have just discussed. So this constraint must has to be satisfied. And if power balance equation is not achieved, we have to update the system lambda. So next value of system lambda will be equal to previous value of system lambda plus delta lambda, and the delta lambda will be calculated from this equation. So delta lambda k is equal to lambda k minus 1 divided by summation I is equal to 1 to k pgi k minus summation I is equal to 1 to k pgi k minus 1 multiplied by pd plus pl minus summation I is equal to 1 to k pgi. So this will give us delta lambda. That delta lambda will be added to the previous lambda to evaluate the new lambda, and based on this new value of lambda, we will again solve this equation number 2 and calculate PGs again, right? So return to step 3 and continue the calculations until final convergence is achieved. So after the final convergence, we will calculate the penalty factors of the two generators, and L1 will be equal to 1 over 1 minus partial PL over partial PG1. L2 is equal to 1 over 1 minus partial PL over partial PG2. These two partial derivatives have already been evaluated in this step, right? So this is partial PL over partial PG1, this is partial PL over partial PG2, and L1 and L2, which are the penalty factors, can be calculated. After that, we can evaluate the incremental fuel cost functions of both the generators. So let's solve an example, and then we will check our result, right? So in this example, we are given two generators connected at the two buses, and the total load of the system is 500 megawatts, and we have to evaluate the system lambda, the transmission loss of the system, penalty factor, and incremental fuel cost functions. These are the incremental fuel cost functions of the two generators. This is A1, B1, these are A2 and B2, this is PG1 and PG2. These are the B coefficients, right? And we have to initialize the value of lambda first, which is AT PGT plus BT. And then we will substitute this value of lambda in this matrix and solve these two equations for Pg1 and Pg2. And then we have calculated the values of Pg1 and Pg2. And then we have to calculate the power loss. And then we have to check if this power balance equation is satisfied or not. Since we don't get 0 at the end, so we have to update our lambda, and then we have to solve this equation again based on the new value of lambda. and check our results. So this problem will be solved in an iterative manner, for which I have written a MATLAB code over here. So for the same problem, I have written this code. This is our B matrix. This is our A1. This is our B1. This is similarly A2 and B2. This is power demand. This is the base. K is equal to 1, which is actually the iteration count. So it is initialized with a value of 1. The initial value of lambda is considered as 0, and PGs are initialized as 0. This is P loss, which is also initialized as 0, and lambda at 2 is actually calculated using the expression which we discussed in our previous lecture, and error has been initialized with a value of 1. Then we will use this while loop, and in this while loop we have put a condition on the error. So as long as the error remains higher than 10 raised to power minus 6, this iteration will go on. And this is our A11, A12, A21, A22. These are the actually entries of this 2 by 2 matrix. Okay, so this is our 2 by 2 matrix here, and we have established this matrix in these 4 steps. So these are the 4 entries, and we have established this A matrix based on these 4 entries. Similarly, BB1 and BB2 are the entries of the column vector at the right hand side, which you can see over here. And this is our column vector at the right hand side. Similarly, this is PG. This is the column vector of PG, which will be calculated by line solve command of the MATLAB. So this will give us the values of PG1 and PG2. Then we will calculate PL. So PL is calculated using the P loss formula, and then we will evaluate the error. This is the power balance equation. If our error remains greater than 10 raised to power minus 6, we will proceed towards the second iteration. So as the iterations go on, at some point we will see our error becomes less than 10 raised to power minus 6, and in that case that loop will be terminated, and we will get final values of lambda powers, loss power, similarly penalty factors, and incremental fuel cost functions. Okay, so you can write this code by yourself as well. And now I am running this code, and after running this code, you can see I have obtained my results. So this is the system lambda, which is 9.8392. This is my PG1. This is my PG2. This is my PL, which is the lost power. Since my load is 500 megawatts, so in this case, you can see PG1 is 190.1522 megawatts, PG2 is 319.0408 megawatts, and this is my power loss. If I add these two powers, I will get 509.1930. So out of this power, 9.1930 is the lost power, and the remaining 500 megawatt will be delivered to the load. So power balance equation is satisfied. Penalty factor of the first generator is this number, penalty factor of the second generator is this number, and incremental fuel cost of the first generator is this dollars per megawatt hours, and incremental fuel cost of the second generator is $6.4306 per megawatt hour. So this is how we can solve optimization problem by using lambda iterative method or lambda iteration method, and by using these iterations we can calculate the final values of all the generators and the total loss which is occurring in the system, such that some power is lost and the rest of the power is delivered to the load. And I hope you have understood the concepts which are discussed in this lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.